Hi, I'm recording this webinar or online lecture to provide an overview of some concepts that we're from reading, as well as to use our class time more efficiently. In this, we're going to look at friction and forces at an angle. Few objects are truly smooth. Perhaps there's glass or ice that approach smoothness, but most items, even that seem smooth to the touch, actually have some microscopic degree of roughness. In the case of this box sitting on an incline, we look at this area that I've just highlighted in red, and the grooves are interlocking with each other. Because they interlock with each other, it's difficult for it to move. One may try and apply a force to the right. However, the two grooves lock together. It's unable to move. We call this static friction. It's not moving. If you push on it with 10 pounds, it pushes back with 10 pounds. If you push on it with 30 pounds, it pushes back with 30 pounds, much as we saw in class today. However, once it starts moving, we have kinetic friction. Again, as we saw in class in the lab, kinetic friction happens when an object starts moving. On a microscopic level, these little bumps over here start bumping one over the other, and it's a little bit easier to move. Let's look at the relative idea of friction. It first depends upon the relative roughness of the surfaces. A smooth surface such as ice will have much less friction than, say, for instance, sandpaper. So we call this the relative roughness. The second part is how hard are the surfaces being pushed together. The harder you push the two surfaces together, the harder you jam those two ridges together, the more difficult it is to move. And so in this case, we'll call that the normal force is a good catch-all. How hard are the two surfaces being pushed together? Finally, our third idea would be simply what we would call whether the objects are moving or not. Again, from what we saw in the lab, we have a lot of friction when they're moving, not much when they're not. So whether we'll say moving or not. Friction's a real concern. It either can cause things to move or stop things from moving. Leonardo da Vinci in the Codex Atlanticus over 400 years ago did discover what friction depended upon and wrote about it, but he also found that it does not depend upon the speed of movement. Once you're moving, it doesn't matter if you're moving slowly or quickly, the friction is the same. The other thing he found it doesn't depend upon the surface area in contact. Even if we flip something on its side, the pressure between the two surfaces will be double, but there's less surface area. So fundamentally, it doesn't depend upon how much surface area there is in contact. We want to write an equation, and we already touched upon this in class. Just to make it easy, the most general idea, friction, we can remember where F is, lowercase f is for friction, is equal to mu, as the cat would say, the Greek lowercase letter mu, times n. In other words, friction is fun, one might say. Well, you may not think that, but this would be the most general statement. However, we do make one idea here. First of all, for static friction, we'll note that the static friction, F sub s, is less than or equal to the coefficient of static friction times our normal force. This is a little more specific. Or, in the case, we can look at kinetic friction, or once it starts moving, F sub s equals mu k times Fn. Again, the static friction means that if you're not pushing on a table, it does not push back. Hence, we have this idea of the less than sign here. On the other hand, we look over here, we can then look over at the mu times s times Fn, so you can push harder and harder, and it will push back with an equal and opposite force. So static friction can vary. It depends on how hard we're pushing up until a certain maximum. Next, we saw the graph much like that we developed in class. We could see over here, we could push, in this case, we have no motion. Our frictional force was pretty close to what we saw in the file cabinet. As our volunteer pushed harder, it pushed back with an equal and opposite force. If you push with 30 pounds, it pushed back with an equal opposite force. It did not move, but then when it started moving, it moved a lot easier. Once you start slipping, it's a lot harder to stop slipping. Because of this, we can think about that mu s is always greater than the mu k. We could think about who won the Revolutionary War. Of course, US greater than UK. Just another way of memorizing this. It's always harder to start an object moving than it is to keep it moving. The coefficient of friction is going to relate how much normal force, how much friction there is for a given amount of normal force. I'm just rewriting the equation from the previous page, F sub n. These are strictly empirical, and I will put over here their FYI. You'll either be given them, or have to derive them, or probably won't ever see them again. But it effectively tells us how to things relate to each other. So something like in human limbs, our human limbs have almost no friction in them. So that 0.01 tells us there's no friction. If you have rubber on wet concrete, that's your car tires. Good rubber on wet concrete, a fair amount of friction, but rubber on dry concrete, even more friction. So you can see the idea is why dry surfaces are better than wet surfaces. How much friction you're going to be able to get. Again, FYI, not necessarily on the test, for your information. Let's think about an application of friction. On a car, you have a certain amount of gravity, mg. Under ordinary circumstances, your friction, your normal force, is going to be exactly equal and opposite to gravity. There may actually be some lift on the car which reduces this, so no spoiler, we get a certain amount of friction. And keep in mind, the static friction which enables the traction of the car for us to behave is going to be equal to mu s times Fn. So the more normal force we have, the more friction we have, the better the car is able to obtain traction. This frictional thing is here sort of weak, but on a racing car we see the really large spoilers over here. The idea, we have the same free body diagram as before, the same mass times gravity. However, we're now going to add a spoiler. The spoilers are like an inverted airplane wing which pushes the car down. So we can say here we have the force of the spoiler. Because of this spoiler, we now have our normal force is actually bigger. We have more downward force. We have both gravity and the spoiler. Therefore, we have a bigger upward net force, and therefore our static friction increases and our car gets better traction. So the whole idea is the spoiler pushes the car down into the ground at high speeds. Gravity works to push the car down into high speeds. We get better traction. Some sports cars, racing cars have that as well. There's a slide here about rolling friction, football hits that are in your notes, but we're not going to talk. We'll talk about those in class. These next slides you don't necessarily have in your notes, but we can look at them, and this is for the last page of your homework. When we're pulling on things, like here we have Calvin's dad pulling on Calvin and his Hobbes in a wagon. When you pull on here, Calvin's dad is pulling up at an angle, as we can see right over here. Because of this, he's pulling both vertically and horizontally. Let's look at the example of Calvin's dad. We'll assume Calvin's dad is pulling at a force of 100 newtons at an angle of 60 degrees above the horizontal because he has both an x component and a y component. We also can think about that our gravity in this case, we'll say maybe we have 200 newtons of gravity pulling us down. And frictional force we have, well, we don't exactly know what that's going to be, but we'll just say 50 newtons for now. In the case of Calvin's father, this x and y is actually pulling us in two directions. So because of this, we could say that Fx over my total force, adjacent over hypotenuse is equal to the cosine of 60 degrees. So when we solve for that, Fx, my horizontal component, now becomes 100 newtons times the cosine of 60 degrees, and if we solve that, we end up with 50 newtons Fx. My vertical force over F is equal to the sine of 60 degrees, and again, we'll go through and solve that. Fy is equal to 100 newtons times the sine of 60 degrees. So Fy is equal to 87 newtons. In this case, we could now look over here, and we could say that the sum of all the forces in the x direction is equal to his forward force, Fx, minus friction equals ma. So in this case, our forward force is 50 newtons, minus the friction of 50 newtons equals mass times acceleration, which tells us we're not speeding up or slowing down in the horizontal direction. The vertical direction, on the other hand, the sum of the forces in the y direction equals Fy is pulling up, plus the normal force, Fn, which I'll label over here, Fn, minus mg, and we don't want it to accelerate, we don't want it to go up and down, so it's constant velocity. I'll say all my forces have to add up to 0. So in this case, Fy is going to be 87 newtons. That's Calvin's dad pulling up, 87 newtons, plus the normal force unknown, minus 200 newtons equals 0. So if we solve for this, the normal force now equals 133 newtons. He is effectively lifting this wagon up off the ground, causing it to be lighter, and because he causes it to be lighter, Calvin weighs there's less normal force, there's less friction, it's easier to move. Anyway, thank you very much. This last problem should enable you to do your last page of the homework. Thank you very much.